Well, then here we go. So this is what we did yesterday. We've already filled this all out, and it is 100% paramount that you start these questions thinking about narrowing down cases, and generally speaking, are you type 1, 2, 3, or 4, and then specifically which of the cases you are. And you're going to narrow it down from 8 to a much smaller number very, very quickly. And if you're on the front page, the questions happen you're done pretty quickly, I guess, unless you're case 5, because there's some work to do for case 5. But if you're on the back, if you're case 5 or on the back page, you have a lot more work to do. Okay, and that's typically how it plays out. So we've already got all of this done. If you don't have all of this done, you need to do this first. Otherwise, a lot of what we do isn't going to make a ton of sense. If you were away yesterday, it was only a couple of you, but we talked about this thing. We basically talked about if all 3 are parallel, you're in type 1. And like I said, you're going to be done very quickly. You're just comparing d values, and then you're done. You're going to state your solution. We'll see an example like that. If 2 are parallel, you're either checking, are they parallel and coincident? Are they the same plane, written in 2 different ways? Or are they parallel and distinct, in which case there's no solutions. Again, you're done. If you're case 5, your solution will look a lot like one of the 4 examples we're going to do. If none are, yes. Oh, sorry, yeah. If none are parallel, you're on the back of the page. Right away, you're on the back and you're one of the 3 on the back. And there's a test you can do, and we talked about this yesterday. Do you have to do this test? You don't. I think it's a good idea. It's fast to do. You have to know about the test, because we might ask you to, without solving, determine what's happening with the system. And in that case, you'll have to do this test. This is a new test, and it's called the triple product. So for those of you that weren't here, you just need to know what this is. I'm not going to get into it in a lot of detail, but I'll do a little refresher. The triple product tells us if the 3 normals are coplanar. What does coplanar mean? Essentially, it means if I'm looking at just 2 planes, do they meet at a nice even corner? Now, whether it's 90 degrees or not doesn't matter. We've talked about that. The angle at which they meet, we don't care about in this case. Or are they like skewed, you might think of them. Now, they're still going to cross if they skew, but they're going to cross not in a nice even corner way. That's how I think of it. Okay, so if you've got 3 planes, they're either all coplanar to each other, and you can see that in both of these pictures, or 2 of them might be coplanar or might not. All 3 might be skewed to each other, but if just one of the 3 is skewed, you're in case 8, and they're going to meet in a point. And the triple product is the test that tells us if that's true. And the only other nice thing about it is if you do it, then you kind of know what to expect algebraically to happen. And if that doesn't happen, you've got to check. That might catch a mistake that you've made somewhere. So that's, to me, a good reason to take the time and do the triple product. And this is the triple product. We're going to do it several times, so we'll get to it later. But you cross any 2 of them and dot it with the 3rd. Okay, and you check to see if that's 0. So you were supposed to do this exercise yourself where you come up with equations of all of them. If you didn't do that, that's okay. We're going to take a look at this demo. This demo is basically the same. Oh, and somebody pointed out to me that there is a bit of a mistake in a demo online. So when I get a chance, I'm going to try to fix it. But basically what happens is if you type them in and you get something unexpected here, what you could try is just trading places of your planes. So switch plane 2 and 3. And then it'll probably work. But I just have to go, the logic is kind of complicated, and I need probably a half. Those of you that have done computer programming, you know that sometimes logic is complicated, and I'm going to have to go back and play with it to figure out to make sure it works in all cases where 2 of the planes are the same, but 1 is different, lots of different cases, so it's a pain. So I'll get to that. But for now, my version of this little applet has the extra bonus where I can click on these buttons. Yours was missing these buttons, and it'll just give me the cases. So this is the first case where the 3 are parallel and distinct. And it's such a nice visual. I get a lot of joy out of just spinning this around and looking at how parallel those 3 planes are and how nice it looks. And they just move in unison. I love it. And there's no solution to that one. If you weren't here Friday or you weren't here Monday, you'll also notice that some people think case 2, where it's hard to tell, but 2 of them are the same. You can tell by looking at the equations. And 2 of them, I think, are right here on this plane. And some people would think that's infinite solutions because those two cross an infinite place, but no, that's no solution because we only care about where all three planes meet in the same single location, right? So this is no solution, but two of them are coincident, and the other is parallel and distinct. And then case 3, you can see there are infinite solutions. The solution is the plane, and all three are on top of each other. And if you look at those 3 equations, you can see why. So coming up with 3 of those would be super easy. In fact, I wouldn't be surprised if those were the 3 that lots of you came up with. X plus y plus z is 1, 2x plus 2y plus 2z is 2, and so on and so forth, right? Case 4, now we see 2 are parallel, and the third cuts through the first 2. And so you don't have 2 solutions that are lines, you have no solutions because all 3 do not meet in any location, right? So those are the easy ones where you've got no solution, or maybe you've got infinite solutions, but you're basically done in 30 seconds to a minute if you're doing a question like that. If there are 2 questions on the test, I would expect one of them to work out like that, because I'm not going to give you 2 long ones, not likely. One's going to be shorter, and then one's going to be a long one, right? Case 5 has a solution. It's a line. There's the equation of the line. And so we're going to learn how to find that equation, but we're going to do that after. But you can see that 2 of the planes are coincident. It looks like plane 1 and plane 3 to me. And plane 2, all I did for plane 2 was change the y value to a negative, and that was enough to make it cross through the other 2. And so 2 of them are on top of each other, right here where this blue plane is, and the third one, the pink one, I think that's how it is at least, cuts through the other 2, and so all 3 meet in a line. So that's one of the cases where you have a solution that you have to algebraically solve for. Okay. Case 6. This one's nice. There were a couple people in Math Help yesterday at lunch that were trying to do this, and I challenged them because I don't know how many of you actually went and did this, but coming up with the equations for 6 and 7 is a worthwhile exercise. It's good thinking just for properties of planes and normals and cross product and dot product and algebra in general. So I would encourage you to do that. And case 7 is probably the hardest of all 8 cases to come up with equations. You have to calculate them to work out that way. And I think the students that I were talking to were like, okay, yeah, we could do that. And I'm like, whoa, whoa, whoa. I don't think it's that easy. It's not trivial to just discount it like, yeah, we can figure that out. No, you got to actually think through it. Making this one work, case 6, probably isn't too bad. You could come up with your normals, pick random d values, you'd probably get lucky. Not necessarily, but probably. I think that's what I did. Okay, but you have to make the normals coplanar, and from there you probably figure it out. But it's nice because if I can get this rotated the right way, you can see the triangle that they form and how they make 3 distinct lines. One's up here, one's here, and the other one's over here. Right? So it's kind of nice that way. This case where you can see the triangle that they make. Okay? Not too hard to come up with. Case 7 is the hardest one. Again, it has a solution. There's a solution. In this case, it's a simple solution. And all 3 are crossing in like a star pattern. And they all cross in the same line. So you have one solution. That's a line. Case 8, people think is the special one, but it turns out it's relatively easy to come up with examples of equations that follow case 8. Be a little bit harder to make one where the point is close to the origin. If you come up with 3 random ones, like if you just type in 3 random equations, there's a good chance they're going to cross in a point, but it'll probably be big and way off the page. So actually locating the point of the origin would be, or close to the origin would be a bit harder, but you could just zoom out. Does that make sense? So there's your visual of your 8 cases. I might post this too if you want to click through and look at all 8 cases on your own sometime, or you can use the other one and type them in. Like I said, I think it's an important exercise. Any questions before we continue? Here we go. This is the one that if you did the practice, you've already done it. Our first task is to what? Compare the normals. So I'm going to write them out. What do you notice? They are all parallel. They are all scalar multiples of each other. You don't have to write out the normals. I don't think it's a bad idea, in particular if you're going to end up doing the triple product and that kind of stuff, because you're a little bit less likely to make a mistake than looking at the coefficients in here, but you don't have to do this. But you do have to do this. So if I take 2 times n1, that equals negative 2 times n2, which equals n3. Whichever normals are scalar multiples of each other, make the statement of how they are scalar multiples of each other. And you don't have, I'll sort of talk about, actually I'll do it in green when it's not a necessary part of the solution. So therefore, the 3 planes are parallel. And we have narrowed this down at this point to case 1, 2, or 3. Again, you don't have to state as you go in your formal solutions on quizzes or tests or whatever which case it is. You don't have to memorize the cases. You will not have access to this sheet while you're doing the test. But for our lesson, I think it's a good idea. And my thinking as I go is in green, because every step of the way I am narrowing down the cases. And if you want to go back and look at the note and see exactly when we knew what we knew, that's why I'm writing it down. Okay? But all you need is the final therefore statement that includes all the necessary parts. So what do we look at now? If I know I'm type 1, case 1, 2, or 3, all I have to do is look at the d values. I don't do anything else. And what do you notice about the d values? Anything? Ah, right, good. But if I notice that I multiplied the first normal by 2 to turn it into the third normal. So if I multiply the whole equation by that same value, it's got to be the same value. 5 times 2 is also 10. So what that means is 2 times plane 1 equals plane 3. But multiplying plane 2 by negative 2 gives me negative 20, not 10. So the second plane, or the third of the 3, however you're thinking about it, doesn't work out that way. So then I say not equal to k times plane 2. Therefore, we're case number 2. 2 of them are parallel and coincident. The other is parallel and distinct. And we're done. It's as easy as that. Like I said, this one would be super fast. So this is the therefore statement that you would be required to make. Therefore, 2 planes are coincident. The third is parallel and distinct. And we say no solution. It's a 3-part statement. The third part is the solution if there is one. If there isn't one, you leave that out. And there's only 2 parts. That make sense? Folks, I would be very careful playing around with the wording of these. People always like to say it their own way, but then they miss some important detail, and what they're saying is not the same as what I'm saying or what we're supposed to be saying. So you be careful if you're going to change up the wording of these statements. Best thing you can do is just kind of get used to the way that I'm saying it and say it the same way. But, as long as you say the same thing, I don't care about the words you use. Don't do it in Klingon. Any questions about that one? Short and sweet. Next 3 are going to be a little longer. So while you're writing down the question, I'm going to do the normals. And you can, if you have time, you can write them out now, or you can do it later, or like I say, you don't necessarily have to. I do think it's a good idea, don't get me wrong. What do we notice? Emery, what do you think? Not parallel. None of these normals are scalar multiple. If you write down the normals, you can just say no scalar multiples. If you don't write down the normals, then I don't know what you're talking about, so you would have to say no normals are scalar multiple of each other. So that is a required statement. I want that said at the beginning of your solution if that's true. What you don't have to say, but what you are thinking is what Emery said, which is, therefore, the planes, sorry, I should say no planes parallel. So what just happened? We flipped our page over. All of the first 5 cases are gone. And we have narrowed it down to 3 possible cases. Case 6, 7, or 8. Right? And it happened just like that. We didn't even have to look at the d-values. We don't have to look at the d-values. You notice on the back of the page the d-values are not applicable. They're irrelevant once you get to the back of the page. Okay, so now what do? We check the triple product. And we did discuss this yesterday. This is not required if you are doing a full solution, but I do recommend it. I'm going to do it quickly because I've already done the actual values, but of course I would be, and I always do N1 cross N2. Like I don't know that you could look at the 3 and decide which 2 you're crossing because it's going to be easier. If one of them has a 0 coefficient, maybe, but I don't know. You're probably wasting more time thinking about that than you are just doing it. So if you remember the cross product, which hopefully you do, you write out the coefficients in the right order, y, z, x, y, and actually do the cross and subtract, right? But I'm going to skip that step and jump to the solution. So 5, -2, -3, dotted with the third, which is 2, 3, 1. And so 5 times 2 is 10, 2 times 3 is 6, 3 times 1 is 3, 10 minus 6 minus 3 is 1, which does not equal 0. So we have a conclusion to make at this point. So I'm going to make it, but you wouldn't be required to do this as part of your solution. You just need the final therefore statement. But what do we conclude? Like this tells us something pretty big. Not true. It is the last case. If you look back at our sheet, when the triple product is 0, is when they're coplanar. When the triple product is 0, they are coplanar and you're case 6 or 7. If the triple product is not 0, you are case 8. No, it's not. It's 1. Yeah, it was 1. Yeah. Yeah. If it was equal to 0, then you'd be correct. It's not case 8. You'd be case 6 or 7. But it is equal to 1. It's not equal to 0. So my conclusion is, therefore, the 3 planes are not coplanar. Or the 3 normals, I should say, are not coplanar. Not planes you wouldn't talk about as being coplanar, right? So they intersect, the 3 planes intersect at a point. And in other words, this is case 8. And now we have to figure out how to solve these. Any questions so far? And whether you are case 6, 7, or 8, or 5 for that matter, I guess, you will be solving. How that solution plays out depends on which case it is. So if you are expecting it to be case 8 because you've done the cross product, you will expect it to work out a particular way, which we're going to see momentarily. Otherwise, you're going to be surprised when it happens, and it's up to your comfort level with this stuff if you want to do the triple product or not. Solving for case 8, believe it or not, isn't the hardest one, or isn't the one that's newest. It's fairly straightforward. It's going to, I think, be fairly familiar with things you've already done. It's not too bad. There's one little detail that you need to know, but once you've got that, it's a lot like what you did in grade 10 solving systems. It's the other cases where you're solving for a line that's the most new to us at this point. So the first what I'm going to do is it's kind of tedious, but I'm going to rewrite these because I've got a bunch of other work in the way. And I'm going to call these 1, 2, and 3. And there's a well-known fact in mathematics that if you have 2 unknowns, you need at least 2 equations to solve that system, like you saw in grade 10. If you have 3 unknowns, you need at least 3 equations. If you have 4 unknowns, you need at least 4, and so on and so forth. Okay? So we have 3 unknowns, x, y, and z. So you can't solve this with the skills we have, at least, with just 2 equations, unless you get lucky. But we have 3 equations, so we can solve this system. Does that make sense? So how do we solve it? Well, first of all, I'm going to examine the 3 equations, and I'm going to look for one of the variables that I can eliminate. So you pick, it doesn't matter x, y, or z. I'm going to look for an easy one. I notice that I've got 3z. I notice I've got 1z and 1z. So I can easily eliminate z, so I'm just going to do that because I notice that's what's easiest. But you might think about x first and you might eliminate x. That part doesn't matter. So I'm going to do equation 3 minus 1. Wait, what am I doing here? Sorry, I'm going to change that. You could do z's. I'm going to eliminate x. I'm going to do 1 minus 2. So z would work. X would work. Either way, doesn't matter. So x minus x is gone. 1 minus negative 2 is positive 3. Z minus 3z is negative 2z. 4 minus 0 is 0. I guess I chose that one because the 0 makes it a little bit easier. And I'm going to call that equation 4. So we just not randomly, but conveniently chose 2 where we could eliminate either x, y, or z. So choose any 2 equations and eliminate x, y, or z. Yep. Is
that the equation of the line where 2 of the things are crossed?
No. Because I could have taken those same 2 and eliminated y, and it would give me a different equation. And so, you know what I mean? Now, here's the trick. Now, you must choose 2 other equations. So we did 1 and 2. I can do 1 and 3 or 2 and 3. And in this case, because I eliminated x, I have to eliminate x again. This is the only thing you need to know and remember. Everything else is the same algebraic kind of steps we've already done. Choose 2 other equations and eliminate the same variable that you did in the first one. So in this case, x. So I'm going to take equation 3 and leave it as is, which is 2x plus 3y plus z equals 9. And I am going to do negative 2 times equation 2. And because I set it up so they have opposite signs, I'm just going to add them. 2x negative 2x, obviously that's gone. This gives me 7y, this gives me negative 5z, and this gives me 9. And I'm going to call that equation 5. Now what do we have? Everybody okay with that? Systematically, we chose 2 separate pairs of lines And substitution, elimination, like however you choose to do it, probably not substitution with 3 variables. Generally speaking, we don't do it that way. Elimination is better, but whatever. And you eliminate the same variable twice in 2 different pairs. Now what do we have? Take a look at equations 4 and 5. What do we have? 2 variables with 2 equations. This is exactly a system like we had in grade 10. Does that make sense? So I've got y and z, and I've got y and z, and now you just solve it like you did in grade 10. So I am going to eliminate z's because it's going to make the numbers a little bit smaller. So I'm going to do equation 4 times negative 5, which gives me negative 15y plus 10z equals negative 20. And I'm going to do 2 times equation 5, which is 14y minus 10z equals 18. And I'm going to add them together. Negative y equals negative 2y is 2. What do you think? It's not too bad, right? That should, I think, feel familiar and reasonable in terms of the kind of stuff you've been doing for a few years. Do you think so, Simo? Okay. Now what do? Now we just take that y value and start working our way back up through all the equations to find the other 2 things. So I've got 2 equations. Like now we know y. And I've got 2 equations, 5 and 4, that have a y and a z. So if I sub into one of those for y, I can solve for z. Then I've got y and z. I can sub back into one of the original 3 equations to get x. So that's what we're going to do. So I'm going to do 6 into 4, which looks like 3 times 2, subbing in the y value, minus 2z equals 4. So negative 2z equals negative 2, and z equals 1. Is that okay? And I'm going to take 6 and 7 into equation 1 because it has all coefficients of 1, so it's going to be easy. So x plus 2 plus 1 equals 4. Subtracting 3 from both sides, x is 1. And now we're done, and now is where you have to make your 3-part final statement. All those other therefores that we're drawing conclusions was just modeling our thinking. By all means, go ahead and write them. If you accidentally memorize the cases, by all means, make notes to yourself. This is case 4. This is case 5. Like, go for it, right? But the required statement is this final one. Therefore, the 3 planes intersect at a point. There's one solution, and the solution is 1, 2, 1. Any questions? Should we do a couple more? Why not? So again, I hope you're okay if I get a head start here and start writing out the normals. No scalar multiples. Once again, first 5 cases gone. We're on the back of the page. And look what happened this time. So last one, the triple product was 1. In other words, not 0. So we knew we were case 8. In this case, our triple product is 0. So we are either case 6 or 7, and there's no way to determine which without just solving. So we're going to start solving, and we start solving the same way we did in case 8. Like, it doesn't make a difference. So again, if you hadn't done the triple product, you'd be proceeding the same way regardless. But I will do a little conclusion off to the side here just to show my thinking. Okay, so 3 normals are coplanar. So the 3 planes either intersect in one line or 3 distinct lines. And in this case, in this situation, we are either case 6 or 7. Like I said, we don't know yet. Okay? All right, let's go for it. Like I said, it's the same thing, so we kind of already know how to do this. And remember, the trick here is just to quickly look and see what do you think is easy to eliminate, which variable. And I see that I think the only one we have here is 3z and 3z. And I've got a negative 1z there, so that's going to make that part easy. So I might as well do that. So I'm going to do 2. No, I'm going to do 3 minus 2. So 4x minus x is 3x. Y minus 2y is 3y. 9 minus 13 is negative 4. Eliminated z once. This is the trick to this. You have to eliminate z again. If you didn't, you'd have 2 equations in 2 different variables. And you'd probably be like, what's going on here? I've got x and y in one, and I've got y and z in the other. What am I going to do? Eliminate y, but then you're going to be left with x and z. Like, you're going to go around in circles. So hopefully, if you did that by accident, you'd realize that you've gotten nowhere. But if you didn't, then you might be in trouble. So it's good to know that you have to eliminate the same variable twice. So I'm going to multiply equation 1 by 3, and I get 6x plus 9y minus 3z equals negative 6. And I'm going to use that with equation 2, which is x minus 2y plus 3z equals 13. And I've set it up so the z's have different coefficients, so I'm going to add, and I get 7x plus 7y equals 7. I had a lot of questions from the Block A class. You know, I from this point, I did one thing, and they were saying, could you do something? Yeah, of course. Like, the specific steps of the algebra doesn't matter. You know how to solve systems of equations with substitution or elimination. You do what you feel most comfortable with. So somebody said, oh, could we divide by 7 here? Sure. X plus y equals 1. That's an easy equation to work with. Why not? Go for it. I'm not going to do that just because I didn't do it before. I won't do it again. I'll be consistent. But like, that probably is more efficient than the way that I'm going to do it. What I'm going to do is I'm going to eliminate x's. So I'm going to turn both the x's into 21s. So I'm going to do negative 7 times equation 4, which is negative 21x minus 21y. But if you're looking ahead, you already know what's going to happen here, plus 28. And then I'm going to do 3 times equation 5, which gives me 21x plus 21y equals 21. And I'm going to add those together, and what happens? 0x plus 0y equals 49. So what happened? 3 distinct lines. We figured out that this is case 5. No, sorry, case 6. Right? So there's no solution, so you're done. And this is the same kind of interpretation that we've seen all the way along. So this is never true. 0 does not equal 49. So this is case 6. No solution.
Do we get something like this if we solve for like something else then? Like,
Yeah, you would get the same. If you eliminated x's, you'd still get a similar statement. Okay, so therefore, the 3 planes intersect in 3 distinct lines, and there's no solution. We're going to do one more example. Any questions before we get to it? So we've seen what happens if the lines are all parallel. It's pretty easy. If the lines are parallel, if they're all coincident, again, you're done. Very quickly, you would notice that all 3 planes are just scalar multiples of each other, and you would say infinite solutions, the solution is the plane, right? You would say the 3 planes are coincident, infinite solutions, solution is the plane. Just the plane that you have the equation of, right? So you're still done very quickly. So if all 3 are parallel, you're done quickly. If 2 are parallel and distinct, you notice that very quickly and you're done, there's no solution. If 2 are coincident and the other cuts through them, you're going to solve similar to how we're going to solve, how we're solving now, and you would find the equation of a line. If all 3 meet at a point, we've seen an example of that. If you get 3 distinct lines, now we know what that looks like. The only thing we really haven't done, we're not doing all 8 cases together, but all the ones we haven't done will be similar to these 4, in other words. So the last one that we haven't seen is when they all meet in a line and we're solving for the equation of that line. That's the last thing we don't know how to do. So obviously, I think it's safe to say this one's going to work out that way. It's going to be either case 5 or 6. We'll see what happens. There were a couple of people in Math Help doing this yesterday, and I heard them just talking to each other and say, let's see if we can figure out how to find the equation of the line. And I kind of said, I mean, great for thinking that. It's not the kind of thing that you could probably come up with. It's not actually even that hard. It's simple. It's not intuitive. There's nothing about it, I don't think, that you go, hey, let's try this. It's just, you wouldn't happen, right? So you kind of need to see this once to know what to do. But once you've seen it and practiced it a few times, hopefully it's not too bad. So again, let's get this part out of the way because we kind of know what's going to happen here. I can see that there are no scalar multiples, so it's not, whoops, it's not on the first page, it's not case 5. So this works out to 9, 6, -3. Again, I'm not doing some magic system where I'm doing this in my head. I already did it. And this works out to 27 plus 18 minus 45, which is 0. So once again, the 3 normals are coplanar. and the three planes intersect in one line or three distinct lines, we are either case 6 or 7. Like I said before, it doesn't matter what you, like which of the cases it is, solving begins the same. And you get to that point where you either get 0 equals something or y equals something or whatever, and then you interpret your solution and you continue from there. Okay? So I'm going to do the same thing. I'm going to do 1 minus 2. So it looks like I get 3y plus 6z equals negative 1. And I'm going to take equation, so I eliminated x, so I got to eliminate x again. So negative 3 times equation 2 gives me negative 3x plus 3y minus 3z equals negative 12. And again, you have to use the other equation. You can't use the same two equations. That wouldn't make any sense, obviously. I hope that's obvious. 3x plus 3y plus 15z equals 10. Add. I get 6y plus 12z equals negative 2. There's my equation number 5. Negative 2 times equation 4 gives me negative 6y minus 12z equals 2. I will add those together and look what happens. 0y plus 0z equals 0. Again, we've seen this before. We know what this means. So therefore, there are the lines meet, or the planes meet in a line. We are case 7, right? Yeah, from our sheet. Okay, so what do we do from here? Oh. All right, here we go. This is like the most important part of the entire lesson, where we get to this stage and we realize that it's going to be a line. Maybe it's case 5 since a line, and you do the same thing. And here's what you do. You pick, it's got to be one of these two. So in this case, y or z. I wouldn't choose x because that wouldn't be as helpful as choosing y or z. Okay, so because we've already narrowed it down to a couple of equations, I'm going to choose one of those two. Whoops. And I'm going to choose z. We often choose z just because it's the third. I don't know why, but if it wasn't in these two, then you wouldn't be able to. And we take it and we just set it equal to some parameter, and we usually use t. Parameter like parametric equations kind of thing. Okay, so choose one variable and set it equal to t. And I'll call that equation 6. And I kind of do the same as we did when we solved for a point. We take this and we start subbing back into equations above to figure out what the other things are. So I will sub this into equation 5 because it's right there on my screen. So 6 into 5, and I get 6y plus 12t equals negative 2. And then solve, in this case, for y. Or solve for whatever remain. Don't solve for t. Solve for whatever the remaining variable is. So I will move the 12t over, and I get 6y equals negative 2 minus 12t, and then divide both sides by 6, and I get negative 1/3 minus 2t. Now I have an expression for z and an expression for y, and I can take those and sub them into either any of the 3 original equations that still have an x left in them. So I'll pick 2 because it's all coefficients of 1 and it's going to make my life a little bit easy. And I get x minus y, which is negative 1/3 minus 2t, plus z, which is t, equals 4. And I start solving this. So I'm subtracting 3t, and 4 is 12/3 minus 1/3 is 11/3 minus 3t. And believe it or not, we're done. How are we done? Because it might seem curious that we're done. You're like, what do you mean we're done? We haven't even done anything yet. Okay, a few of you have your hands up. That's fantastic. What do you think? Daniel?
We can just write it in parametric form.
Those are the parametric equations. There's your z, there's your y, there's your x. That's our solution. Generally, we write it in vector form. I am going to write it in parametric form because I think it's more obvious when we write it out that way. So x, x is right there. X equals 11/3 minus 3t. Y is negative 1/3. Fractions are a bit of a pain, but we don't have to do much with them. So, and z equals t. So you're always going to get one of them just be simple like that. And the other two will be a result of whichever parameter you chose to set equal to t. Does that make sense? Therefore, the 3 planes intersect in one line. There are infinitely many solutions. And the solution is the line x, y, z equals 11/3, negative 1/3, 0, plus t times negative 3, negative 2, 1. Yes?
We expressed it in parametric form and named it like L, like you have. Can we just say solution is the line L?
I would say, I wouldn't write it twice. I would say the solution is the line and then write it that way. And if you wrote it in parametric form, yeah, I mean, you would get away with it. You know what I mean? I would just, instead of writing it over here and then saying is L, I would just write it there.